okay? Set aside some extra time to do homework and study for this quiz, because it's kind of like in this course there's a lot of ideas, and now there's algebra involved and a lot of things going on at the same time. So just want to warn you that if you want to make it through this part and really retain it, set aside the next 2-3 days, set aside extra time for this course, okay? All right, so let's talk about the homework that you're turning in. Page. No, nothing's in the right place. Why does it move things? Let's try it there. Okay, so, and then I kind of forgot to remind you, but we didn't turn in the homework Friday. Did you bring Friday's homework? Okay, most of you are nodding. You don't have a fearful look on your face. So let's turn in Friday's homework first. Friday's homework. Pass those in. We're doing these separately. Don't mix in today's homework. For Fridays. Okay, so in terms of writing the heading, if you could don't wait until this first 5 minutes of class to do that. So when I say turn in the homework, this should be all ready. It should be in a minute. Okay, so try to remember that. Don't wait until this kind of couple. And I may have trained you to do that, but so in those minutes before class, or when I'm making some announcements at the beginning, start putting your heading in. Friday's homework. Pass them in. Okay, and then so while we're talking about today's homework, go ahead and get it ready to turn in. Any more Fridays? Okay, so let's talk about where did it all begin? So Friday's homework. What does it all begin with? The example that we've been looking at. What's that? And what does that represent?
Area or
yeah. What is that function about?
The output is area of
the output is area of a square. Input is side length. So those are exact area function. That's where we began, right? Our exact area function. And how can we see that as an accumulation function? How can that be thought of as an accumulation function? So input, you put in 1.5, it spits out the area of the square. But how can we see that 1.5 in the area of 1.5 squared 2.25? How can we see that as accumulation? Because that's what we're calling it. We're calling it accumulation. Yeah, Melody. Okay, so we could set it up as an integral, but just kind of as an idea, this function, how can we think of it as accumulation? Yeah, Janae. So it's from what to what? So if I'm using an example of a side length of 1.5.
So as the area of the side length increases from 0 to 1.5.
Okay.
That area would accumulate.
Whatever that area is. Yeah, excellent. So as the side length increases from 0 to 1.5, all along that, as we did that, the area would build up little by little until it reached the final area of 2.25. Whatever squared, whatever our units are. Okay, next, so where do we go from there? So we have our exact area, and we're on a journey here. What's the next step in our journey? Next route, or next approximate what? Approximate accumulation. So do you have an image of what that would be? I've got delta x set at 1 right now.
It would be like a step.
Step function. Approximate accumulation.
Piecewise.
Okay? Oh, no. What is that? Fixed. I did not mean that. I meant this. Kind of. Right? So we have a piecewise, and each of those pieces is based on what really important idea? Each of those pieces is an average rate of rate. So it's based on an average rate of change, and those average rates of change then give us the next thing, which is what? Approximate rate. Right? So from those red pieces, each of those has a constant rate, and so we can make a step function of those constant rates. And then what was the next thing? And how do we get exact rate from approximate rate? What's the key? Yeah. Let delta x get small, right? So we can let delta x get small. And when it gets very, very small, maybe a little, still want to see it there. Okay, so it's very small, and then that forms the exact rate, right? Forms the exact rate. Okay, so as functions, what was the first function? So going back to that process, what's the first function?
Exact.
Yep, and that was what we called x squared, right? F of x was x squared, the area of a square function. Okay, then from there, approximate area. In the homework, I called it Lx, right? I called it Lx in the homework. And then, approximate rate. That was this, right? And this whole thing, what's the general structure of that whole thing right there? What is that talking about? Yeah, good. They both said delta y, which is calculating what?
Changes in area.
Okay, so but in general, what is that thing? A constant rate of change, or average rate of change, right? It's the average rate of change over that delta x. So based on the x squared, based on our original function, it's calculating an average rate of change over delta x, which we know is the constant rate of change to get the same change in y for the same change in x. It's the constant rate of change to get the same change in output for the same change in x. You better believe you're going to have to write that on your quiz this week. So learn the definition of average rate of change. It's on the quiz, I'm telling you. Okay? In context, right? So there'll be some other real-world context. And in that real-world context, you have to write what the definition of average rate is. Okay? And that's in the list. Okay, and then so from there, how do we get to our exact rate? We let delta x get small, right? And we get the exact rate. And so how does that change this? Yeah, Ross? Yeah, when you have so many intervals, so, you know, you have a gazillion intervals, think of a million intervals, well then just the left x just become the left side of every interval. If they're so close together, so many of them just becomes the continuous value of x, increasing, right? So, as delta x gets very small, Rx becomes this expression. Okay? It's still an average rate of change. It's still average rate of change over a small, it's now over a very small delta x. And when delta x gets very small, then it's indistinguishable from exact rate of change. Okay? As delta x gets very small. Was that, is there a question?
Oh no, I just like just connecting what we learned before
Uh-huh.
about how you're saying like a line isn't really a line. It's just a lot of dots.
Okay.
It's the same concept, like
Right.
why it looks like a line.
Yeah, but if it gets small enough, it's indistinguishable from the line.
Yeah. Exactly.
So like there I've made it 0.03, and that's not even really very small,
So
but
that's
still.
That's why we represent it as like a line, because of the fact that we can't physically.
Right.
But, okay.
That's right. Okay, so now, applying this rule to the expression. So we need to write this. So we have f of x is x squared, and we want to write this. Is there a question?
I did have a question about the first process. It was the f of x.
Yeah.
What was that again? Could you go over it briefly?
What is f of x?
I mean, what was that process? What?
Watch the video. I just did it. So this is the last 10 minutes. This is what I just did. So just watch the video again. Okay, so now we want to write that if f of x is x squared, then we can change the form of this. We can work with this here. So what does this equal if f of x is x squared? So we got to take it one step at a time.
So
If f of x is x squared, what's that right there? Somebody knew. How about? What would that be? If f of x, so what does this function say? It says take the input and square it. So now, what would that be right there? Yeah, Shannon. X plus delta x. So it said take the input and square it. Remember, function is a set of instructions on the input. So you identify what the new input is, and you do the same set of instructions that it's calling for on the new input. So this says take the input and square it, so you take your new input and you square it. Right? And what's f of x?
X squared.
That's just x squared, applying the rule to just x. Okay, and so, yeah, go ahead.
So I wrote this in my homework, but basically, are you doing substitution, aren't you?
Yeah,
Like, are you, just like do substitution, you're basically just doing a substitution with the input and the
Okay. Okay, so this has nothing to do with use substitution. But we're just based on the function's rule, we're rewriting this. So in a way, it's a substitution because these are equal. This is equal to this. So that's in that sense, it is a substitution. Okay. And then also, you're substituting the old output x. Now you're substituting x plus delta x. So yeah, so you could think of it as substitution. Yeah. Another question.
Do you always apply the rule in this way to get the exact rate function, or is it only something simple like x?
No, yeah, good question. Any original accumulation function is gonna have this same average rate of change function. And so you can do it for it's not for simple functions, it's for all functions.
Well, I mean, when you're actually doing the equations or anything, working it out, is it logical to...
Yes, because we have graphing calculator. You're going to love it. Just stay tuned. Hold on to your hat. Okay, so now, so we've got that. Okay, so now we want to actually work this out, okay? Quickly. So we've got that. So this is like what you're going to have to do in your quiz. Okay, and so I gave you the two possibilities in your quiz. So how do you multiply that first part?
X squared plus 2x delta x plus x delta x squared.
Notice that it's not this is not x squared plus delta x squared. Okay. Gotta know that. This is not x squared plus delta x squared. There's a middle term, 2x plus delta x, okay? Minus x squared all over delta x. Okay, so this is the process that's I'm giving you the two that are on your quiz. Okay? So this is what we're talking about. So where do we go from here? Somebody on this side. Kyle. How can we simplify this numerator? 2x plus delta x? What's our next step in simplifying this? Well, how is it that we can simplify this? You see? Jaina?
You cancel out the x squared.
Yeah, because we got plus x squared and minus x squared, right? And what's left?
2x squared delta x plus delta x squared.
Try again. What's left when you take x squared minus x squared?
2x delta x
Right?
plus delta x squared.
I heard something totally different. So if that's what you said, I apologize. But I heard something totally different than that. Okay, so. All right, from here. What can we do from here? Yeah, Melody. No, because then everything is 0 and we get 0 over 0. So you can't do that here. Alexander.
If I factor out delta x.
You got to get, so here's the problem. If delta x gets really small, it's like we're getting 0 in the denominator. So there's a problem. We got to get rid of that. So factor out delta x, and we're left with that, and then, okay, now Melody, now it's time. Now we can let delta x get small. And what do you get? 2x. Okay, and we say essentially equal to. Okay, the equals with a dot means essentially equal to. So this right here is essentially equal to 2x. So this is a very powerful process because it gives us a very nice form of the exact rate of change. So this represents the process of setting up exact rate, knowing that delta x will get small. But working through this algebra gives us something very simple to work with. Okay, so these are essentially equal when delta x gets very small. Okay, and then that, we look at this and we say, we look at this our exact rate function that we came up with, and it's, look, we got the point 1, 2. And we got the point 2, 4. And it's coinciding perfectly with this algebraic result, 2x. Okay, so 1.6. What is our, so at 1.6, what's the value of our exact rate? 3.2. So we get this. So I want you to take us a minute to talk with the person next to you and interpret this point in the context of the square context, in terms of the area of a square context. What does the point 1.6, 3.2 mean? Go.
No, that's the exact rate. That's plugging that into 2x, yeah. So, and the x-axis as x, the side length increases to 0.6. Rate increasing the area increases. Yeah, and it makes sense too. The square is just a side square. So whatever the length is there, it's twice that. That's the area.
Okay, who wants to give it a shot?
Next is also left.
Gilbert, you want to try?
Sure.
So tell me, what does 1.6, 3.2 mean?
Completely forgot what you just said. Alright, so as the rate of the side length increases, is 1 point. As the rate of the side length is 1 point of the area. Since 1 point side length is 1.6.
Okay.
The area, the rate of the area is 3.2.
So when the side length is 1.6, so let's make big squares. How about kilometers? Okay, so when the side length is 1.6 kilometers, what can you see? So what did you say?
The area is 3.2 kilometers.
The area is 3.2 kilometers squared. Is that right? Some are nodding, some are shaking. Jonathan, what do you think? What does the 3.2 mean? So we've got 1.6 kilometers side or square. What is the 3.2?
Isn't that the average rate of change?
Okay, it's an average rate of change. Yeah, tell me your name here.
Aaron.
Aaron.
It's the exact
Exact rate of change. Exact rate of change. And so what does that mean? 3.2 is the exact rate of change. Peter.
At 1.6 kilometers, the area of the square is changing at 3.2 kilometers per kilometer, or square kilometers per kilometer.
Yes, so the area is changing at 3.2. What are the units on the 3.2? Kilometers squared, is that the units? Per kilometer. Don't cancel anything out, right? Because we want to preserve it like this. Changing at a rate of 3.2 kilometers squared per kilometer. What about at 1.7? Is it still changing at 3.2? So this implies that if we increased to 2.6 kilometers, that the rate would go up 3.2 kilometers, or the area would go up 3.2 kilometers squared. Is that right?
No.
Why not, Nicholas?
Isn't there, because the rate is different?
Right.
Difference.
Our exact rate function is a changing rate function, right? As soon as we move off of 1.6, a significant amount, the rate is different. Okay? So we can think of, just like we're thinking of, delta x getting very small, we can think of a very small interval of side length around 1.6. And for that very small interval of side length around 1.6, the area is changing 3.2 kilometers squared for every unit of side length that it increases. Okay, and we'll keep talking, we'll keep going over that. Does anybody have a question on that? Does it make sense? What's that?
Can you like word it in a different way?
I don't know.
Yeah, sure.
So like what I said was like, at exactly if the side length was 1.6.
Okay.
Then the area of like the square would be changing at the rate of 3.2.
Okay.
Is that like what you mean like? Did I
Yeah.
say it correctly?
Yeah, the area is changing at a rate of 3.2, but the units are important. Kilometers squared per kilometer. Okay, so let's do this. So let's say x is 1.6. This is red. So x is 1.6, and let's say we take a small increase in side length, say 0.002. What can we conclude? So now I've got the sides of the square is 1.6 kilometers. I'm going to let the side length get a little bit bigger, 0.002 larger. What could you conclude based on this 3.2 kilometers squared per kilometer? Brent, any ideas?
Is it that the rate will be slightly more?
Okay, the rate will change, but so because we're in such a close vicinity, we're going to assume for that's close vicinity a constant rate through there. Okay,
Oh.
but you're right. As soon as we get off of 1.6, the rate is a little bit different. But in terms of interpreting the meaning of this, let's say in the vicinity of 1.6, this rate kind of stays 3.2. So then what could we conclude? What would stay the same? Okay, so that's what we're assuming. What?
So you're saying that they're basically the same number?
What's basically the same number?
Well, I'm just going off of the previous class. I mean, if it's close enough that you can't really find a distinction, is it being the same?
But what two numbers are you saying are the same? I don't understand. What?
The 1.6 with the change of the 0.002?
Okay. But we want to conclude about area, right? So this is all about area. We increase the side length a little bit. What about the area?
It's going to increase at that rate, 3.2.
Okay. So if it increases at this rate, what can we say?
That's the same.
So you can't just say it's the same. There's all kinds of quantities flying around here. You got to be very specific with your language, or else no one knows what you're talking about. Okay?
The 3.2, like the area of 1.6 and 1.6.002, those.
Is 1.6 an area?
I mean the side length. Sorry.
Okay, side length's 1.6, and we let the side length increase a little bit. What does 3.2 tell us about what will happen?
Won't it like increase by area of 3.2 over 0.002?
Okay.
Like just by that much. Like the area will increase by that much.
Will it increase by 3.2?
No,
How much will it increase by?
by 3.2 over 0.0.
So to get the change in area, it's going to be 3.2 divided by 0.002.
No, times.
Delta y equals k delta x. Right? So we're assuming a constant rate for a very small change in x. Our constant rate is? And delta x is? So what are we saying? We're saying that changes in the area at this around right around 1.6, this is when the side square is 1.6. Changes in the area will be 3.2 times as great as changes in the side length. So we worked on this, we're working on this a lot, right? So we just got to apply it to this situation. Okay, that means that the change in area is always 3.2 times the change in the side length. So what is that? What value is that? 0.064? No, 0.0064? Is that the area of a square? What is that?
No, that's the increase.
The increase. It's the change. If we were to increase from 1.6, if we were to increase the side like 0.002, our area would go up about this much. Would go up about that much. Why? Because 3.2 means how many? It's the size of changes in area relative to a change in side length. It's relative size, right? It's a rate, so it's a relative size. It's the size of a change in area relative to the change in side length. So if our change in side length is this, our change in area will be 3.2 times as great as that. But then as soon as we move to 1.8 for side length, we have a different rate, right? We have a different rate. Okay, ask me, does this make sense? Is this familiar from like the last month? But it's just now we're in kind of in a different place. So yeah.
I'm confused. At what point does a change in x affect the rate? Is it when we approach 1.7? Does that?
Well,
Because you're saying
the bigger this change is, the more error we'll have here. That's the idea, right? So as soon as we get off 1.6, the rate is slightly different. But I'm talking about a very small change. So we're just going to assume just for a very small window around 1.6. The bigger I make that window, the more error I'm going to get if I use 3.2.
Okay, is there at some point that you would say the error is too great that you've got to switch your? No.
It depends on what this result is for. So in the real world, you're saying, what are we using this for? How much tolerance do we have? Yeah.
We're using the graph on the left for this, then wouldn't y be the exact rate of change and not the area? Or did we use a different?
Yeah, the y, what is the y value at 1.6?
3.2.
3.2. So that's our rate of change. That's the rate of change of area with respect to side length.
Okay, so change in y in this case is area and not rate.
Y, this is our y, this is our area, and this is area per side length. This is rate,
Okay.
remember? This is just what we did in all semester. This is our area function, and this is our rate of change. So our rate of change is 3.2. It tells us that the area at this particular moment, or for a very small window around 1.6, that area is changing 3.2 times as fast as the side length is changing. So if we change the side length a little bit, the area will change 3.2 times as much of that, or close. Now, if I make this 0.1 or 0.2, and we use 3.2, then there will be more error in that increase in area. But for a very small side length, this is a fair statement to make. Yeah.
The part that I don't understand is you're saying that x is at 1.6,
Right.
we're changing it.
Yeah.
But it would still have the same rate, so would y still be x squared? Ignoring the changes that you're making, or is that just?
Well, yeah, y is always x squared. The area of the square is always
So
x
then
squared.
where is your change of y, like, what was the original y? If you're changing
1.6 squared. So 2.56. 2.56 is the area at that moment. So yeah, I don't need to know the area at that moment to ask this question. All I'm asking is, if I increase the side length, how much will the area increase? And that's what the rate of change tells us. It tells us right that 3.2. So this whole conversation is about what is the meaning of this number? What is the meaning of 3.2? What it means is for a small change in side length, your change in area will be 3.2 times as great as it. But it doesn't work for a large. Why doesn't it work for a large change in side length?
Rates change.
Because the rate's changing. Because the rate's changing. Do you see? Is it better?
Is there any way you can relate that back to the accumulation function? Like how, like, is it just the area under the graph? Is that what we're looking at right now? I'm saying, like, if you were to actually draw that on the actual graph, could we do that really quick?
Over here in the area function?
Yeah.
So yeah, in the area function, we could look at the area at 1.6, and that'd be 1.6 squared. Okay, and then we could look at the area at 1.6002, which would be 1.6002 squared. And what could we do to check our answer? Subtract. So this is the area at 1.6. This is the area at 1.6002. So let's do that.
Yeah, that answer's only off at like 0.0000.
It's really close. It's really close because I picked such a small change in x, right? So let's do this. So 1.6002 quantity squared minus 1.6.
Yeah.
You've got 1, 2, 0. Yeah, it's 50.602.
Thank you. 0.006404. Okay, that's the true change in area. We use the rate of change, 3.2. We got 0.0064. So it's very, very close. Okay. So now that we're going the other way, we're going from accumulation to rate. Now we've got this exact rate function. We got to know what that means. We got to know what that rate function is telling us. This example is just to kind of highlight what that number 3.2 is about. It's saying that the changes in area or the changes in y are always 3.2 times the change in x. But it only works in a small vicinity because if we get away from, we change x too much, now the rate has changed. So it only works well in a small vicinity of whatever x value we're at. Okay. So let's talk about some notation and summary here. Okay, so all through this conversation is the idea of limit, okay? So we just established this. We established that that ratio is essentially the same as 2x, which means that thing means they're essentially equal when delta x gets very small. So I'm going to fly through this, so don't try to write this down. If you want to watch the video and write it down, I'm just going to fly through this, okay? So just listen. That also means both expressions are the same. They're both essentially the same for sufficiently small values of x. Okay, and what do we say? That's the idea of there's no number between them. If you have two values that are the same, then you can't find a number between them. So you can't find a number between that expression and 2x if we let delta x go to 0. And so our notation for that is this notation right here. Okay, the conventionally, we use the symbol h for delta x. Okay, so when we use h for delta x, the notation becomes this. Okay, and so how do we say that? So that the expression on the left, we say the limit of this ratio as h approaches 0 is 2x. Okay, so the limit, or you could say the limit as h approaches 0 of the ratio. Either way. And what does that mean? Again, just to review, it means that these two things are essentially equal for a very small value of h. There's no number between them. Or if you found a number between them, then you can make h smaller so that that number that you found before is no longer between them. And you can keep doing that forever. See? You can find, so say h is really small and you find a number between the left and the right. Well, you can make h small enough so now that number that was between is no longer between. And if we keep doing that over and over and over again, we essentially are saying they're the same value. Okay, any questions on notation? Yeah, Peter.
On a quiz or something, if we were to do the notation on the right and we didn't put the dot on top of the equal sign, would that make it wrong?
Yes, or you have to write the phrase for very, very, very small h.
Okay.
Yeah, but if you just left it without the dot, those are not equal because it's assuming that h is some finite value, right?
Right.
So you got to have that. You got to have something that indicates h is very, very small.
So why does H with an arrow to 0 mean that H is very, very small?
You imagine h is getting exceedingly close to 0. So it's as close to 0 as you can imagine. Atomically small values of h. Okay, so just a summary here and a new term. Given any exact accumulation function, that's where we started, right? Its exact rate of change function is called the derivative. So if we start with an accumulation function, say g, then the exact rate of change function is called the derivative of g. So for our example, 2x was our exact rate of change function, right? And that was for the area function of x squared, f. And so therefore 2x is the derivative of f. So what is the derivative? It's the exact rate of change function given its accumulation function. We derive it from, so we derive the exact rate of change from the exact accumulation. Okay, so let's work through another example. Anybody recognize that function right there? 4/3 pi x cubed. So what's the input and what's the output? Nicholas thinks he's got it.
Radius length?
What radius length is?
The input?
Input and output?
Volume of a sphere?
Volume of a sphere. So where do we start? We start with exact volume. And we think of it as accumulation. We can think of that as accumulation, exact volume. And from there we go to build an approximate volume. And from the approximate volume we have constant rates, and we can now over here we have rate of change, right? We have rate of change. And so we can build the constant approximate rate function. And then as delta x gets small, so you notice, so you can watch the approximate rate, watch both graphs, right? Watch the piecewise function and also watch the approximate rate function. The piecewise function does better and better at pretending to be the accumulation, and the approximate rate approaches the exact rate. There it is. Okay, so we now have an algebraic method. So now this isn't, so the line was kind of easy to see that it was 2x, right? That rate function, we could just kind of see, oh, that looks just like 2x, but what's this, right? So that's why we have the algebraic, that method of doing this algebraically, and we can figure out exactly what this curve is, all right? So I want you to do the first step. Apply the rule. Here's 4/3 pi x cubed. You write out the first step. What does our average rate of change function for small values of delta x? We're going to use h now. Use h. What is that first step if this is our function? Go. Put that out. So really, the only tricky part is this part right here. So we can get that right, then we should have no problem building the rest of it. Connor, think you got it?
4/3 pi times the quantity of x plus h cubed minus 4/3 pi x cubed over h.
Here's what he's offered up. Do you agree? Is that what you did? Did you do it in better handwriting than me? I think we can still barely read it. Okay. That's it. So now I want to show you. So this is a cubic. So cubics are a little nastier to multiply out, and it gets kind of ugly. So let me show you why you're really going to like graphing calculator. Now, what I'm about to do is for people who know how to do algebra. It's not for people who don't. Okay? This is for people who know their algebra, not for they don't. So I'm going to take this, I'm going to copy and paste it, write it again. And the first thing is, one thing you can do here is, sorry. So I'm going to highlight. I notice that there's a 4/3 pi in both. So just to get started and make things look a little nicer, I'm going to highlight just the 4/3 pi. And notice a hand pops up. So if I'm just going to grab that and move it to the left, and watch what happens. Okay, it just factored it out. Okay? This is for people who know how to do algebra, not for people who don't. Okay, so now the next step. In here, I'm going to highlight what's in here, because this is really all the work that has to be done, right? And what do we going to want to do? We want to expand that. So if you go up to math, and you do expand, boom.
What?
Okay?
Now we have to do algebra in this class.
No, wait a sec. I didn't want to do that. Listen. What I really wanted to do is this next. I just wanted to expand this, because it did too much. Okay, so I'm going to expand that right there. So I'll go back, expand. Okay, there we go. So it just expanded x plus h cubed. Now we look inside there, and what do we see? X cubed. We got a positive x cubed and a minus x cubed. So then you can go to simplify. It does it. Okay? All right. What from there? What's our, so in order to get the algebra, this is our problem, right? H getting small means 0 in the denominator. Therefore, so look, so you can just grab the h like we did before. There's a little hand. Grab the h, slide it over, comes out. Factors out of all three terms. Okay? And then I could, so I'll copy, paste. All right, and so now I can simplify that.
Do all those commands have to be on different command lines, or you just?
Nope. You could just keep it on the same command line. But I want it to show the whole progression. Okay, so that the h's are gone. All right. What's that? Just move this 3 into the denominator. Yeah, just took that 3 and moved into the denominator. Okay, so let's. I want to move this back in. Okay, I just moved it back in. All right, and then I think we're ready to go. So now once that h is gone out of the denominator, we're ready to say, what is this when h is very, very small? So what is this when h is very, very small? So what will happen to that when h is very, very small? It doesn't care. It doesn't have anything to do with h. It becomes 4 pi x squared, right? When h is very, very small, what happens to that?
0.
Yeah, it gets very, very small. So does that. Okay, so those two things are essentially equal for small values of h. Okay, so what is this expression? That first expression we wrote is the rate of change of 4/3 pi x cubed with respect to x. It's the rate of change of 4x cubed. It's the exact rate of change of 4x cubed with respect to x. You got to practice writing that and saying that in your homework. Okay, we're out of time.
Do you want today's one?
Yes, and then pass in today's homework. Make sure you set aside time for calc. Okay, just while you're walking out. So that curve that we found for the graph, this is the equation for that curve, the exact rate. This curve over here, the exact rate.
So we're not turning it on work?
Sometimes it's
Well, it's just all here divided by 3. So I divided there, right? So it's 3 over 3 is 1. 5 is 30. And then when this goes to 0, then this week, you could do it for 1 week, but like, you gotta go Yeah.
This is today's homework.
Okay, thank you.
Fridays.
These are Fridays?
Yes. I had a question.
Yeah, sure.
This is homework. So just to like get down the process, it's the exact accumulation function, which goes to like it goes to approximate accumulation function, which is a piecewise function, and
Yeah,
then
here.
that goes to the actual.
Picture tells 1,000 words.
Yeah, that's actually.
Okay, so why is that still drawn? What's that? What happened? Oh, because I put that, turn that on. Okay. So first, in this case, exact volume of the sphere. Then approximate volume. That's our average rates, right? Average rates that you're trying to pretend to be that. Why is that? Where is that coming from? Oh, it's because. Turn all these off. Okay, now we're good. And from there, what do we get?
It's gonna be approximate. It'll be approximate rate of change.
What kind of rates?
The rates from the approximate.
Yeah, but what kind of rates are they?
Steps.
Constant rates, right? So each of those pieces of the approximate volume gives us a constant rate. There's the first one, there's the second one, there's the third one.
Okay.
So we get a step function of approximate rates. And then how do we get exact rate?
We make the constant smaller, which is delta
And make
x.
the
goes
changes,
smaller.
right? The change is smaller. Look what happens over on the right to the piecewise function.
It gets smaller, so it gets closer to
It gets
the
closer to the
graph.
actual, and what happens to our approximate rate graph?
It becomes exact.
It forms, right? It forms the exact rate.
And then also like just one more like connection. Is that why like in like regular math classes it's like x cubed and like the derivative is 2x and then
We're doing, yeah, you'll do those in your homework, the rules.
yeah, and like that's the rule, like because this would be an x cubed right now, so that would be an x squared, so that's how
That's
it
right.
works.
So there's these rules, right? We're getting to those very shortly.
And this is my I just wrote my
This is
question.
Fridays or today?
That's today's.
Today, okay.
Yeah. Thank you.
This is Friday. Let's see if I got any more rubber bands left, and that's today's. Russ.
I didn't push, but I forgot it, so
Okay.
yeah, sorry.
Oh, no. That one's still good. That one's still good. So I'll email you the quiz right now. I have it. I don't have the key yet, but I'll get that as soon as I can.
Okay.
Did you think of it?
No,
Okay.
If I think of it later, I'll.
Yeah, email me.
Thank you.